All right, great. So I'll turn it over first to Josh Willis, and we can hear about OMG. So take it away, Josh.
All right. Thanks a lot, Joe. Thanks for inviting me. It's a pleasure to be here and talk a little bit about what we're doing with OMG. I'm going to try and get my screen shared here. So uh, give me a shout if you can see the first slide. Does that look good?
Yep.
Great. So OMG stands for Oceans Melting Greenland, and oh my God, if you're a millennial. We're basically a 5-year-long NASA mission. We're an airborne mission. We have a pretty long list of co-investigators working with us to analyze the data, plan the investigations, and so forth. And we're about halfway through. And I'll give you a really quick update, but first I want to say that all the data from OMG is publicly available as soon as it passes quality control or any processing that's required to make it usable for science. Anyone can grab the data from the website pretty much as soon as we collect it in a lot of cases. So go out and grab the data. When you grab it, shoot me an email and let me know you're using it. OMG consists of 4 different observational campaigns. I'm mostly going to talk about the ocean campaign today, but just to give you a brief overview, one of the really important aspects of the ocean-ice interaction problem is just measuring the seafloor shape and depth around Greenland. And so we had 2 campaigns, a ship-based multi-beam sonar survey, which mapped a whole lot of fjords, particularly in northwest and southeast Greenland and parts of the shelf that had gone unmapped. And then for a little bit broader view, we also collected airborne gravity data, which you can use to invert and learn about the shape of the seafloor and infer some of the depths in places where we don't have the ship data. So we collected a lot of bathymetry data. That data is all available online if you're looking for it. The other 2 parts of the campaign, the bathymetry campaign is finished. So all that data, pretty much all the data we've collected, pretty much all the data we're going to collect, we've collected already. There's also 2 campaigns to measure yearly observations of ice and the oceans. The ice survey involves a radar which provides a digital elevation map over the last 10 kilometers or so of pretty much every marine terminating glacier around Greenland, right at its terminus. So we're mapping the glaciers right at the ocean ice interface. And what I'm going to talk about today is the ocean aspect, where we're also collecting CTD data from airdropped CTDs. These are one-time use instruments. They fall out of the airplane. They land at the surface of the ocean. They deploy a little float, which keeps part of the instrument package floating, and it contains an antenna. Another part of the instrument package looks like a little torpedo. It drops on a very fine wire and can reach all depths all the way down to 1,000 meters. And it collects temperature and conductivity measurements as it falls. It falls at a pretty well-calibrated, well-known rate. So what we actually measure is temperature and conductivity as a function of time. And then we reconstruct temperature and salinity profiles from that as a function of depth based on the timing of when the fall started and the rough or the well-calibrated idea of how fast they fall. The aircraft has to stay in the vicinity for this. It's a radio transmitter, and so we have pretty good range. We can fly away pretty fast and still collect the data as long as we have some altitude. But after about 10 minutes, the probe has fallen all the way to the bottom of its line, and the surface part stops transmitting, pops the floating part, the little floating bladder that was inflated, and the whole thing eventually sinks to the seafloor. So we drop about 250 of these. The plan is to drop about 250 of these in the coastal waters around Greenland. The survey looks something like this. 2015, we actually did not have the aircraft available yet. We were not able to get a 2015 survey started, but we did have the shipboard shipboard CTD, which collected CTD data during the bathymetry campaign in Northwest Greenland. And so we have a whole lot of CTDs in Northwest Greenland, particularly in a whole lot in Melville Bay from 2015. 2016 is what a typical survey year should look like for OMG. Again, we dropped maybe I didn't say this, but the ocean survey typically happens in September. That's when the sea ice is minimum. You can't drop these things with any kind of ice present, or they don't function correctly in terms of sea ice. And so we aim for the minimum of sea ice. This is about 210 or 215. We didn't quite get to drop all the ones that we wanted because we ran a little late into the year in 2016, but we did get a nice even survey all the way around, except the very northern parts, which are pretty well perennially covered with ice. In 2017, we had a bit of a late start due to our aircraft being shuttered during Hurricane Harvey in Houston. We had to switch aircraft a few times, and that put us late in the year. And so we wound up not being able to collect very far north in the northwest corner due to the encroachment of sea ice. But we did get a very solid survey of about 235 probe drops in 2017, covering the southeast and northwest regions pretty thoroughly. So just to give you a sense of a little bit of what we're beginning to see, I want to talk about, I'm going to zoom in really quick and then I'll zoom back out. This next work is stuff that was done by Ala Kazandar at JPL, one of our OMG team members, along with Ian Finty and some other folks we've all been shipping in. But very interestingly, in Jakobshavn, we found that our first two ice surveys of Jakobshavn showed something kind of interesting. This is the, so just to give you a sense of where we are, we're in West Greenland. Jakobshavn is here, the main ice flow in the southern branch. There's also some an ice flow in from the north. But this is a relief map based on the digital elevation data collected from OMG in 2016. And this is 2017. And I'll just flip back and forth a couple times. But what you can see is that in 2016, the ice front was down here. And in 2017, it actually advanced. And if you take the difference of the two elevation maps, you get this. So green here actually shows thickening along the main trunk of Jakobshavn. And it's a thickening by 30-ish meters or so. The end, which is saturated in color, represents the advancement of the edge of the front from here to here in 2016. So this was a bit of a surprise. The very first year we had our recurring measurement in ice in OMG, we saw the glacier advance, which if you look historically at the ice velocity at this point here is unusual. It's the first time in 20 years or so that that the ice sheet seems to have, or that the glacier speed seems to have slowed dramatically from one year to the next. There was a peak in speed in 2014, and then it was in 2017 when the glacier speed slowed rather dramatically. So if we look at some of our CTD data from the region just offshore, we start to see a kind of interesting story. There was a pretty substantial cooling between 2015 and 2017. So the little pins in the map over here show the locations of CTDs in different years from Disco Bay. So the glacier is a little bit off the picture. The glacier edge is a little bit off the picture to the right. But these CTDs were targeted for the deeper parts of the bay and the trough that sort of connects it to the broader shelf. And they're color coded, so blue is 2015, green is 2016, and red is 2017. Likewise, the pins in the Disco Bay area. And so what you can see is that in 2015, it was substantially warmer and saltier in Disco Bay in all these regions. And although I didn't show it here, a similar signal persists all the way to the edge of the shelf down this large trough, which extends to the edge. So there seems to be a broad scale cooling that happened between 2015 and 2016, and especially 2017 in Disco Bay and the waters that we think are probably reaching the edge of the glacier. Of course, because we're dropping these from aircraft and we're in a jet or a C-130, we aren't able to hit any tiny little gaps that may actually occur in the ice in the fjord. So all of our data is offshore of the actual fjord, but nevertheless, this cooling is interesting because it's actually broad scale across the entire shelf. So if we zoom back out to the 2015 and 2017 data in Melville Bay, we can look and see if this signal persists in a much broader area. So I'm just plotting the data from Melville Bay in 2015 and 2017. Here, blue is 2015, red is 2017. And you can see that in temperature, and there's a similar salinity signal, the waters overall have cooled between 2015 and 2017. So this is, and by a degree or two, it's maybe not quite as strong as the signal in Disco Bay, but clearly there was a broad scale cooling that affected the waters all up and down the shelf on this side. So this is a nice, interesting little anecdote over these couple of years. And there does seem to be a clear signal in Western Greenland. However, if we look in Southeast Greenland, we can consider the data from 2016 and 2017. We didn't have the ship down here in 2015, unfortunately, so we only have 2 years of this broad scale data. But what you see if you look at the comparison between these 2 years and places is a big mess. So there's no obvious signal in here. And of course, it's known that there is some stronger eddy activity in these regions, and a large scale signal may not be as apparent or as measurable in here. So this is a place where we have to look a little more closely if we want to see a clear signal. And I think I'll just really quick, since I have a minute or two, talk a little bit about one more region, which is Ingelfeld. This is a large inlet, a large bay to the north of Melville Bay. So there's the question of whether that signal has made it all the way up here. But we took another look at the at CTD data in this region. In 1 year, in 2016, we had a small ship with a single beam sonar. We didn't get a complete area map of the bathymetry in this region, but we did have the ship go back and forth a whole bunch of times, collected a ton of CTD data. This is a wide enough fjord that we sort of expect a horizontal circulation in and out of the fjord. And so we can look at that a little more closely right at the edge, using the CTD data up here. And for this plot, I just took the CTD stations along here on the blue pins as a sort of example, and calculated the geostrophic velocity between each of the 2 stations. And I just made a simple assumption that there was a 0 velocity at the bottom, which I consider to be the deepest common point between the 2 stations. So this is a pretty crude estimate of the geostrophic velocity. But if you look at it, so the vertical axis here is depth down to 400 meters, and the horizontal axis is minus 20 to minus 50 or so centimeters per second. But you can see that in between The southernmost ones, you don't have much going on, but here there's a big eastward velocity. Here there's also a large eastward velocity. And in the farthest north pairs, you have a westward velocity. So the general sense of the velocity between these stations looks something like this, where you have water flowing into this inlet on the southern side and out on the northern side, which is about what you expect from what we assume about the circulation in there. This is interesting because we also have the glisten data from 2 years, 2016 and 2017, and you can see a very slight change in the fronts here between these two glaciers. But if you look at the difference in height, we can see that this glacier is thinning very rapidly, and this one is not doing very much. So this larger glacier has stayed pretty much the same between 2016 and 2017, and the smaller one, Tracy up here, thinned pretty dramatically and retreated a bit. And so if we look in this region, this is just a blow up of the thinning. But if we look in this region at the CTD data and try and see if we can see some implication of what the ice loss from this glacier might look like, we can look at the CTDs from here in the southern part relative to the CTDs here in the northern part, and see a pretty remarkable difference in temperature. So the temperature of the southern CTDs tends to be warmer at depth. This is typical of waters around Greenland where you have a temperature inversion. So we tend to have 1 to 2 to 3, or in some cases 5 or 6 degree Atlantic water at depths below 200 meters. This water is deep because it's salty. So the saltiness makes it heavier and sits on the bottom. It's usually covered by a layer of Arctic water, which tends to be fresher and colder. So you have cold water on top of warm water. And that's what the CTD data prior to the circulation reaching this glacier looks like. After the water passes by this glacier, then it's much more mixed. And so we have our warm Atlantic water kind of getting wiped out, and our fresh Arctic water also kind of getting mixed. And so it appears that there's some mixing going on here. And if you look at the salinities, they're fresher all the way through. So this is sort of suggesting that this glacier is dumping fresh water, not just at the surface, but somewhere down here where it's able to entrain this Atlantic water and mix it up into shallower depths. So the reason for showing this is it's sort of an example of the kinds of things we can do with OMG data. And in addition to looking at the more large-scale pictures like this. And I think I'll stop there because that's plenty to chew on, and hopefully we'll have some time for discussion at the end.
Great. Well, thank you, Josh. That was fascinating. Yeah, I definitely learned a number of new things there, and I hope the audience did too. Yeah, we'll talk about that right after. We'll move on next to Twyla's discussion, if that's okay, and our presentation. And so, Twyla, are you ready to take it away?
Yeah, let me get this screen share started and make sure you can see things.
Yep.
How does that look?
Perfect.
Great. Yeah, so talking a bit about fjord freshwater and zooming in on that, and you can see there below the collaborators on this project. Dave Sutherland, I noticed, is on the call, so maybe he'll end up speaking up if questions come up later. Also Dustin Carroll, now at JPL, Dennis Felixson's at University of Texas, Laura Curl at the University of Washington, and Fiamma Storneo now at Scripps. So first of all, what was our interest in thinking about these problems of fjord freshwater? And we're really asking the question of what that fingerprint of freshwater flux looks like in space and time. We're interested in that for thinking about ocean properties, thinking about circulation, some of those elements that you could see in Josh's talk just now, as well as the influences we're going to have on the biosphere. And I suspect there are other areas too, thinking about nutrient flux or nutrient circulation and other elements like that. And there might be people on the call who have some additional ideas too. And then another element of this is that translation between observations and models. It's common still for models to dump fresh water from the ice sheet into the top ocean layer. And there are groups who are working to improve this, but we haven't had data really to work with in order to make this improvement. All of this that I'll be chatting about today is covered in this paper that just came out at the end of 2017 with a group of collaborators I mentioned. And I'll be focusing in on this for our pilot study, which was here in Sermilik Fjord. And you can see we have Helheim, Fenris, and Midgard glaciers feeding into this fjord. And we're primarily focusing on this fjord region, not as much including the arm here up to Midgard. Helheim is producing most of our icebergs that we see in the fjord here. And you can see the wide collection of CTD casts, data that's running from 2008 up into 2013. And there are also a couple of moorings which are not on this map, but are located here in different locations mid-fjord. Sermilik Fjord has some different conditions in summer and winter, and also I want to talk about the different sources of fresh water that we get in the system. So a basic graphic of the system, not to scale. We have here in summer our runoff that's happening both terrestrial and subglacially. So subglacially, we're getting runoff creating these meltwater plumes, and then we also have ambient melt there along the terminus. And in our study, we're using regional atmospheric climate model data in order to get at those numbers. Other people might approach it in a positive degree day method or some other kind of surface mass balance modeling. Another area of besides this, just this runoff component is actually the terminus melt itself. And we created some new model results. They align well with other results that are out there. So there's not new news. It seems like at least the different techniques that we have around today are finding fairly similar numbers for terminus melt on these glaciers. And then the third source of freshwater melt being icebergs. And that's what we had developed our new method for looking at iceberg melt so that we were able to capture where freshwater is being produced at depth and at different locations in the fjord. So here in summer, I just want to point out some of the features of the system. We have a developed hydrologic system over on the ice. We still have our ice melange that we see year round, surface waves, a mixed surface ocean layer on top, and this deeper ocean warm layer below. And that's in contrast to what conditions generally look like in the fjord in winter, where we're losing our most of our subglacial discharge and then the terminus melt related to that here. So we still have ambient melt contributing. The distribution of temperatures in the ocean changes, and I'll show you another plot of that later so you can get a better idea of what that looks like, but those look quite different from summer to winter. And we develop stronger winds in winter, both these along coast winds and over here with our katabatic winds. We also have sea ice coverage. In Sermilik Fjord, we don't see full sea ice coverage, so we generally do have these areas of open water as well. And because we have these higher winds, we get bigger waves in winter in those open water areas, which influence some of our melt processes. So what these melt processes are on iceberg that we're looking at, we have our above water melt processes that depend on solar radiation, air temperature, wind, these sorts of climate metrics. And for this study, we are taking that from ERA interim reanalysis data. Then at this ocean surface, we have wave erosion, and that's related to our sea surface temperature, our sea ice coverage, which is affecting our waves, and again, the wind also affecting where waves are. And that sea ice concentration, we're pulling from Landsat image analysis. It's actually something for maybe other researchers who are on the call to think about, but we really don't have a good product at this point for getting sea ice concentrations close to the ice sheet. We had considered some other remote sensing products, but they tend to show that you have full sea ice coverage in the fjord when in fact you don't. So we needed to go to a different analysis for that. And then here in the subsurface region, our submarine melt is primarily dependent on our ocean temperature and our ocean water velocities. And so those we're getting from CTD casts and from moorings. And I underline velocity here. That'll come up again later as a kind of particularly hairy data point where you can imagine CTD casts, much like the ones that we saw Josh talk about for OMG. We can gather data and get at these kind of discrete time slices of information, but getting longer term ocean water velocities is much more difficult, and the data there is much more sparse. So we're lucky in Sermilik to have quite a bit of field data on both of these ends, having 2 moorings and having CTD casts for many years. So what does that information tell us? I'm pulling out here data from March 2010, which is representative of winter, which we see here in the dashed lines, and then August 2010 representative of summer in the solid lines. And you can really get a sense that we have somewhat similar temperatures at depth in both seasons. You're seeing a difference between melange and mid-fjord, between the lighter color and the darker color lines. But you can also really get a sense of how different these ocean temperatures look in that upper roughly 200 meters between the seasons, and also some sense of that influence that the melange has, particularly in the top 50 or so meters. And if we go ahead and feed all of this data that we've pulled into this iceberg melt model and just look at what this means for individual icebergs of different keel depths, you can see this is what we get. And what's happening here is we have lines of summer melt along an iceberg flank and winter melt. And these are looking at, you can see these different keel depths as we look at different iceberg sizes. And we get a transition zone here. And that transition zone is due to a velocity shear zone. So we actually have our ocean water moving in one direction up here and in a different direction down here. And that's creating this kink in our iceberg melt. And you can get a sense that in summer, relative to winter, we have almost as much melt happening in the upper portion as the lower portion on these icebergs in summer, whereas in winter, we're really concentrating our melt relative to along the whole surface in those deeper layers. But there's only so much utility in understanding what's happening on a single iceberg. So what we did was we took Landsat data and some work that had happened in Dave Sutherland's lab for detecting icebergs, and we used that information to get iceberg distribution data. And so with that iceberg distribution data, we were able to classify how many icebergs there were in the fjord, their size, and make approximations of what their keel depth would be based on their surface width. And in that way, we're able to take this information that is coming from a single iceberg and scale it up to what that we see as far as melt happening for the full fjord. So in this case, we're summing up the melt that's happening from all of the different icebergs of different sizes throughout the fjord. And you can really get the sense that our icebergs tend to be shallower keel depths. So we're losing some of that big melt signal we have here. Although in winter, we're still highlighted in blue, you can see we're getting melt at depth that it approaches to what we see in this mid-surface layer. We always have this spike at the top as we're contributing all of our above surface melt as well as our wave erosion. Wave erosion actually creates the highest point values for iceberg melt, but because it influences such a small part of our iceberg depth, it doesn't come out as the most important thing overall for iceberg melt. And then in summer, you can see that we get much larger spikes here in our surface as in comparison to the subsurface. And what we ultimately find is that across these seasons, we have 68 to 78% of our melt produced at depths below 20 meters. So that's really in stark contrast to that more common practice of taking our melt and putting it into our surface ocean layers. Of course, this is looking at where our melt is produced. So we wanted to get a kind of rough estimate of what this would mean for where our melt might stay. And there's a lot more work to be done on this portion of it, but using some of our more simple models of plume, and water buoyancy, and identifying where we have different stratified layers in our water column, we could see that in winter we have a stratified layer here at about this shear zone, and almost 40% of our melt during winter is produced and then likely remains below this 170 meter zone. In summer, we have a stratified layer there as well as closer to the surface. And so in summer, we can see that about 60 to 70% of our melt is produced and likely remains in this 20 to 160 meter depth, and around 5 to 10% below this 170 meter depth. So the vast majority of our water from icebergs is being created at depth, and it appears that most of it probably stays there. So that's a good indication that we need to be moving forward on figuring out how to translate this kind of development of freshwater at depth through our iceberg column into what our ocean models are receiving as boundary conditions, or into how we're thinking about coupling ice and ocean models. There was some interesting work that Fiamma Straneo and her group have done in Sermilik, finding that there are some similarities. In fact, they look very similar as far as water conditions just inside the fjord and outside the mouth over the continental shelf. So that gives us some confidence that these sorts of numbers that we're producing inside the fjord might be translatable out into the open ocean water as it's transversing over the shelf there. But our interest was not just in what's happening in icebergs, but also what was happening for the full freshwater flux within the fjord, and the role of these different components. So in order to cycle up to a full annual cycle, we needed to add more information about what our ocean was doing. And so this is a January through January plot of ocean temperature that we constructed using the mooring data. And you can really get a sense of the difference that we have here and the representativeness of those sorts of March temperatures of kind of the coldest surface period, and then that transition into these warmer conditions, especially here around September in early fall. And one question that I'll bring up again later is thinking about how we can continue to increase knowledge of our ocean conditions throughout the year, and coming up with ideas of what's happening in different seasons and different locations, and continue to really increase our ability to create temperature maps or ocean current maps like this that can capture some of the seasonal variability. I think is going to be really important if we want to think about scaling this work up to all around the Greenland ice sheet and other places in both poles. So using this and feeding this information then into our iceberg melt model, we're getting at monthly iceberg melt, and then we're combining that with those different sources of information I mentioned earlier for these other freshwater sources. And this is what we end up with. I'll start here at the bottom where we have terminus melt, and this is a combined total from Helheim, Fenris, and Midgard. In mid-fjord in Sermilik, there is some other ice that has a marine connection that's not included, but you can get the sense here are totals there. And when we're thinking about freshwater in a fjord like Sermilik, terminus melt is not one of our primary factors. We step up about an order of magnitude for looking at terrestrial runoff that's dropping into this fjord from all of that area of open land beyond the edge of the ice sheet. And then again, another order of magnitude step up here to what we see as subglacial discharge from all glaciers. One thing that was really interesting in looking at subglacial discharge versus iceberg discharge, Helheim produces the vast majority of solid ice for this fjord, but the runoff basins for Fenris and Midgard are not small, and they actually produce a significant portion of this subglacial discharge. So thinking about some of the less active glaciers around the ice sheet is important when we're thinking about subglacial discharge and runoff, as opposed to thinking about solid ice discharge. But you can really see that all of these factors are responding to high air temperatures. All of them are peaking in the summer, and really it's our air temperatures that are controlling the melt signal for all three of these elements. And that's in stark contrast to what we get from icebergs. Here, we have our modeled monthly iceberg melt, which is here, our blue line with our gray zone here of uncertainty, and we've added our CTD coincidence iceberg melt calculations. And you can get the sense that at no point do we have kind of a single time when iceberg melt is producing the kind of discharge that we get from subglacial discharge at a single time. But if we integrate over this whole year, iceberg melt is the largest producer of fresh water in the Sermilik Fjord. And this peak is offset by about 2 months because icebergs are responsive to our ocean temperatures, not to our air temperatures. And likewise, as we drop off into winter, early spring in here, we continue to get substantial iceberg melt in times when all of our other freshwater sources are producing negligible additions to the system. So there's this very different time stamp of iceberg melt as the main contributor in the fjord. And then you can imagine, I haven't visualized it very well here, but you can imagine that we have a very different spatial fingerprint as all of the runoff, terrestrial runoff, terminus melt is happening at these fjord boundaries, whereas these icebergs are really moving around in that fjord and adding this melt at depths throughout the fjord and all along it in map view as well. So they're really a unique producer of fresh water. Of course, now we'd like to think about how this work can be scaled up to the full ice sheet, and we can start to understand what different sources of fresh water are going to look like across the ice sheet and how they're going to compare to each other and how that's going to change over time. And this is where that topic that I brought up earlier about velocities really becomes difficulty, and not to be clear, not ice velocities, which you can see in the map here, but actually ocean currents and how they're moving. And these 5 different fjord areas that I've outlined here are the only areas that I'm aware of that we have ocean current data, which is, as you could see, really important for the melt that we're getting on icebergs. We're caring about the temperature and we're caring about ocean water velocities. So we've thought about techniques for, in these locations, using those in situ measurements for ocean velocities, and the potential to use these locations to start to explore how we might use data from ocean models and then make some assumptions about information from water velocities there off the shelf and what that might mean for water velocities within these different fjords, so that we would have information to feed into our iceberg melt model. So you might imagine producing kind of two different levels of data analysis, where in fjords like this, where we have better in situ information, we can produce a higher level product telling us about freshwater production, partitioning out our different sources and having a higher confidence for the numbers that we're producing, and a second level product that might include more estimates of what ocean water velocities look like, with higher associated uncertainties. But certainly, I think beginning to use this kind of information here, and the information that I was talking about earlier about where freshwater is produced at depth, and starting to incorporate that into ocean models and see what kind of influence that produces on the system. Is that the kind of thing that we're just worried about if we're thinking about local processes? Is it important at regional processes? Is it important for basin scale processes? So those are questions that really, I think, need to be explored on the modeling side beyond what we've done here. So the quick take home, iceberg melt is an important contributor in fjords like this, where we have high solid ice discharge. It can be the primary freshwater source, with most of it being produced at depth, and half to all of that remaining at depth, depending on the time of year. And also we see this peak at a very different time of year. So it's sometimes models also tend to say as soon as ice has left the ice sheet, it's instantly transitioned into becoming liquid freshwater. And we know that's not true. And perhaps there's some important elements about that timing of solid to liquid transition that we need to think about. So a few of the questions that I raised, and a couple others, how we can increase our knowledge of subsurface ocean properties in space and time. How will freshwater flux change with climate changing, and how will different sources become more or less important at different times? And what does that influence look like on different dependent systems? So that's all I've got.
Great. Well, thank you very much, Twyla. That was also wonderful. So thanks, Josh. Thanks, Twyla. That was very informative. So I'd like to now open it up to discussion, and maybe to try to bridge the gap a little bit between Josh's talk and Twyla's talk. I'll start off with a question. Twyla, you fairly asked how you can scale up your technique to other glaciers. And in your paper, you also mentioned that the technique you mentioned may be of most relevance to the fjords that are iceberg choked, which are often associated with glaciers that are big names because they've been changing a lot. But what about glaciers that, or fjords that aren't as iceberg choked? How do you, and perhaps the ones in North Greenland that maybe have almost near perennial sea ice in front of them, how would you approach modeling them, and what do you expect the differences might be going in sort of the freshwater distribution and the relative effect on circulation?
Yeah, I think that you hit the nail on the head as far as kind of the wide variety of fjord systems that we have. And we can think about the importance of icebergs. It's not just whether you have a quickly moving glacier that's going to produce a lot of icebergs, but then it's also about how long those icebergs are staying in place. So there are some places where you might have glaciers that are not moving as quickly, but because of the fjord geometry, you have icebergs that are staying in place longer, versus some locations you might have a lot of production of icebergs, but they might get fairly quickly moved out of the system. And groups like I know Lee Stearns at Kansas and others have been working on improving our iceberg distribution maps. Mm-hmm. And I think those really play the biggest role in identifying areas of importance for iceberg melt, rather than just thinking about metrics on the ice side as far as ice velocity, etc. But certainly in areas where you don't have icebergs that are produced, or where they're very quickly moved out of the system, you can imagine that that's when you're losing kind of that freshwater production that extends out through the year, and you're really getting a concentration of freshwater production that's happening during summer. Of course, some areas in the north, you have a very short melt season. So then you might imagine that those order of magnitude jumps between surface runoff and terminus melt are going to start to drop, and you're just generally not going to see the same kind of freshwater flux as you're going to get in some other systems. So there is a potential for a lot of variability around the ice sheet, and I think mapping iceberg distribution is going to be one of the most helpful things for that, rather than some of the ice sheet side metrics.
Not just size distribution, but maybe persistence in time.
Yeah.
Okay.
Yeah, what the method that we took was looking at discrete images. So we were not following icebergs as they were moving around the fjord. We were really looking at discrete points in time and building up a map that way. And really, I think that's an okay approach to take, because that's a much more tractable problem than sorting out the following of icebergs on top of it.
Yeah, great. Well, thank you. I'd like to open up the floor to other questions. We've got 33 folk. I'm sure there's some thoughts. Perhaps a question for Josh?
Joe, I've got one.
Oh.
Twyla, this is Tim Bartholomew. Thanks, that was a great talk. I was wondering if your time series of iceberg melt contributions seem to follow the seasonal cycle of ocean temperatures. Is that because there are always so many icebergs in Sermilik that there's always the capacity to melt more icebergs, or to what extent do you need to take into account the availability of icebergs in the fjord to melt?
Yes, in the case of Sermilik, we have a lot of icebergs year round. So it's very much a matter of what the ocean conditions are, because there's ice available to melt. But certainly that would look different in some other locations, and there might be actually, Dave Sutherland might have a comment on this, but there might be areas too where you can imagine that during open water periods, your icebergs are moving around in some fjords or near coastal regions. And then as you get sea ice, they're being held in place. And that's, of course, also changing how they respond to the ocean currents and what melt looks like, whether they're moving with those ocean currents or whether they're being held in place by sea ice. So those kinds of seasonal differences in how many icebergs you have and how mobile they are does make a difference. But overall, whatever ice you have there is going to be responding to your ocean conditions primarily.
Yeah, and there really isn't any kind of seasonal cycle of iceberg density in Sermilik Fjord. It just must be tiny. Yeah, thanks.
Michelle Copez knows how to use the Zoom system better than I do, and she has her hand raised for a question.
Yeah, it's a very pale hand, but thank you. Thank you for two excellent presentations. I have a question for Josh and a question for Twyla. Josh, I was kind of intrigued. You showed the kind of compendium of temperature profiles from 2015 to 2017, and that there was this cooling in Disco Bay below 200 meters. But I also noticed that there's an inverse in the surface waters between 2015 and 2017, or 2016, I don't know what it was, where the surface waters are warmer earlier, right? In the earlier years, and they cool off. And I was just wondering why, or was there a timing difference in when they were measured, or kind of
You're talking about right here. I think
Yeah.
it's my screen,
Yeah.
right? Yes. There was a slight timing difference. The um, uh, the 2017 data was taken in late September. The 2015 data was more like midsummer, like July or so, June, July, something like that. So there was a small, it's still in the same quarter or so, but there was a small seasonal difference. And so that could explain some of what's going on. Certainly at the very near surface, the atmospheric conditions were probably very different between these two time periods. But just below the surface in the top 100 meters, this could be a seasonal difference. So yeah, it's the picture of what's going on is a little murkier in the surface, partly because we don't have the time resolution to really say what's going on. But I think down deep, these changes are probably bigger than the seasonal differences that you expect at these depths between sort of July and late September. So yeah, we probably are getting some pollution of the seasonal signal into this kind of analysis in the very near surface.
Okay, and then it was the same thing in Disco Bay, right? Where you comparison, you also see that difference. So that's also you're attributing that to the timing.
Right, and yes, this is probably some due to differences in timing, although the 2016 and 2017 data, they were within a month of each other. So this is probably due to interannual changes as well. But generally speaking, I think as you go nearer the surface, you expect more variability on shorter time scales. So aliasing of signals in terms of looking at differences between one year and another probably gets worse as you go near the surface.
Gotcha.
But there are some, this is an interesting difference as well, and something that if we get some more data in Disco Bay, we'll certainly be interested in investigating. And I think also it might be clearer in a TS diagram than on these two plots.
Cool. And then Twyla, I was fascinated with this idea of what Tim asked, how representative is Sermilik of these other fjords? And I was also kind of intrigued by the fact that terminus melt was so tiny in Sermilik Fjord. And I was just wondering, to what degree does the volume of icebergs in a fjord, do they have an inverse relationship to the amount of ambient melt the amount of warm ocean water that can get to the terminus to cause that ambient melt, and whether whether the keels of these icebergs, it's not only the melting of the icebergs that's causing the mixing, but the keels can cause mixing in those upper layers? Has that been looked at in the models, or any ideas?
Yeah, I think that's a great question as far as kind of how all of this iceberg melt further out in the fjord is really affecting the heat that's able to access the terminus. And that's something that I haven't looked into further. And Dave, do you have any comments on that? Another thing is Ellen Enderlin also has some nice work that's thinking about iceberg depth and iceberg melt using a different technique, and I think also has the potential to start asking those kinds of questions, but has not yet either. So I think there's much more to be done as far as fjord circulation for asking those kinds of questions, although it's certainly makes intuitive sense.
Yeah, I would just agree with that, Twyla. I think you said it pretty well. And I think, the proof will be when we compare some of these initial results to when we try to do this in other fjords, I think, in other glacial systems, then we'll get a better sense of the parameter space of how important iceberg melt is compared to all those other sources that Twyla mentioned. So.
Actually, I have a quick question for Twyla if there's still time.
Yeah.
My question is, how do What sort of effective velocity do the icebergs move with when they're not sandwiched in by the melange? If they're free to move, do they kind of drift at the upper layer's velocity or the lower layer velocity, or some average between?
Well, it is going to depend on their keel depths. So that is, of course, influencing how much they're being affected by the upper water velocity versus, because you remember they're going in opposite directions, and
Right.
that's a little bit confusing, but it helps explain why as they get deeper, their upper layer melt actually increases. Because they're feeling more of this opposing velocity. So there's some kind of funny things having to do with keel depth in there. And that is really going to influence it. For ones that are shallow enough to just sit, for example, in the upper water layer, I don't know off the top of I can't remember. Dave, do some of your measurements suggest that ones that are shallow enough to just, for example, be in that surface water velocity, are they going to move at those speeds?
Yeah, they tend to move with the depth average of whatever ocean velocity they're feeling. For these largest icebergs, once you get to smaller bergy bits, the wind definitely plays a bigger role, and they don't necessarily move with just the ocean. But for all the ones we're looking at, they're big enough that we would. There's theoretical scales you can come up with where the ocean matters more than the wind, for example. So it's just the depth average. And so if there's no shear in the water column, if there's no vertical gradient of velocity, then they'll just move around and there won't be any, relative velocity to them.
Is it also their cross section at different depths that's important, or are they pretty vertically uniform? The kind of graphics you had them kind of coming down to a little point at the bottom. So does the cross section of the velocity layer that they feel also matter in terms of that depth average velocity?
Yeah, it certainly would. Iceberg shape is a outstanding research question. And I know Dave has recently been working on taking structure images to think about iceberg shape. And there's been sort of a smattering of other bits of research over time thinking about iceberg shape, but that continues to be kind of a hard nut to crack as far as an average shape. And it certainly does influence how much area you have feeling one kind of water property, be it temperature or velocity versus another.
One last quick point. I don't know if you guys have looked at it or aware of it, but there a long time ago, like 10 years ago, there were some efforts to do iceberg inventories from altimetry data. Because the radar signal changes really dramatically when the altimeter hits an iceberg, and so there are some iceberg inventories. I don't know if they've been updated to use newer altimeters and higher latitude altimeters, but I know there was some work on that a while back.
Yeah, and actually some of the data that comes off of Operation Icebridge now suggests that we might be able to see iceberg shapes in that, and then you're kind of, matching your imagery and your data and figuring out what part of an iceberg you're looking at. And there's also been work using upward looking imagers. So you have a mooring and you're looking up and you're seeing, what is this keel depth that's passing over? And then the challenge is kind of understanding what part of an iceberg you're looking at. The graphics that I show are not very well representative of actually the kinds of iceberg shapes that are used in the model, which tend to be more blocky and less cone shape. That was just a matter of graphic design.
Great. Well, thanks, guys. I see Tim has his hand up again. Do you have another question, Tim?
Yes. Yeah, I had a question for Josh about if there's anybody who's doing this sort of kind of almost real time as the OMG data comes in, who's doing the data assimilation into ocean circulation models to lean on that data to kind of create more fully distributed views of ocean properties.
Ian Finty and Ichiro Fukumori at JPL are tasked with doing that. I don't know how far along we've gotten so far because I keep distracting Ian with all kinds of other fun stuff to do on OMG. But we could definitely use help with that.
don't look at me. Yeah, but so is that still going into Echo 2 or ASTI or the?
I don't think yet, but there are plans to do that.
Okay, but that's coming.
Yes.
Okay, thanks.